Okay, so here we go, tutorial 3, non-isothermal unsteady state design. And so in question 1, part A is just the derivation, which you can read, of course, from the notes, right? So, but I just want to sketch this CSTR so that we can get the labels right and just understand the physical meaning of all these things. So I'm just going to work here in, okay, so we've got the CSTR. And we've got flow through the CSTR. And then the CSTR is also jacketed. And let's just give a different color here. Yeah. Okay, so you've got your jacket temperature. So you've got some temperature in here, TA. And you've got an inlet temperature here, Tin. And in fact, let's just use a different color for that. So you've got your reacting fluids temperature T in here, and then in here is temperature T. So let's just look at the variables. Yeah, T inlet, TA, all defined, and FA naught, I guess we can write here as well. So you've got a flow rate of your reactant component, and there's some conversion also that we've accomplished in that reactor. Right, so you accomplish conversion X in there. So that's just to list the variables. And if you follow the derivation in the notes, you'll see that we classify two types of energy contribution. One being the contribution from the reaction itself. So in the reactor, due to the translation of the species, so if you like, your chemical potential energy is converted to thermal energy due to the reaction. So there's a certain heat, and we think of that as heat generated. So G of T is due to the reaction. And of course, it might actually be the case that energy is being taken in. In other words, it might be that the reaction is actually cooling the reactor. So, but anyway, we'll just define G of T to be energy being that the temperature is increasing, and then it might turn out that G is negative. So anyway, that's the energy due to what's happening in the reactor space. And then we can also write a term for the energy removed from the space. So we can write R of T is due to the jacket. So those are the two things happening, right? Heat is being generated by reaction, and heat is being removed by jacket. And it might be that heat is actually being added from the jacket and R is negative. So anyway, whatever it is, that's how we've defined it. And now in this problem, right, so as I say, you can go ahead and just look at the derivation in the notes, but try to do it yourself also without looking first. So it says in the actual calculation part of this question, the reaction is quite nonlinear. And so the G of T curve shown is not the same as the one we're used to. So most of the time when we showed it in the notes, we drew G of T something like this, right? And that was because we were looking at a first order reaction. So for other types of reaction, which might be non-elementary, might have complex kinetics, even if it is elementary, then you'll get quite a different shape for G of T. So in this problem, we are given G of T. So it's given here as a graph. And then we are told also that our heat removal rate is also something that's not straightforward. And this might well be the case that we have some kind of weird heating going on. So we might have some kind of heating that doesn't behave according to the traditional heat transfer media. And whatever that is, it's eventually turned out that R of T actually looks something like this. And just from the form of this equation, it's a quadratic in the temperature. You can see other temperature variables here, but these we consider to be, in a way, constant. So if you look at our picture here, we've got the inlet temperature to the reactor. So this we consider as being something external to the heat transfer that's going on there. So in terms of your inlet flow to the reactor, that we consider to be under the control of upstream processes and maybe some other control and things like that. So we are not really thinking about changing T in. So we regard that as a kind of constant. So that's out. And then this TA is more of a concern to us because the temperature you accomplish in this jacket is a function of the temperature in the reactor itself. And it's also a function of how fast you are passing fluid through here. It's a function of the inlet temperature here to the jacket. So like we said before, you could identify a TA in here and a TA out, and then there's an average TA in the jacket. But even so, we still regard TA as another constant in this whole system. So that this is more of a simplification that we are using here. So under that, everything here is constant. So A and B we are taking as just constants. And so R of T is indeed a function only in terms of T squared. So we expect this to be a kind of quadratic, right? So that's just in terms of understanding sort of the physics of the problem. So in this question, we are asked to describe any particular dynamics features of interest in terms of controlling your temperature. And we want to sketch out, it says concentration time, but it really should be temperature time. So this is an error in the problem. In the statement, this should be sketch the temperature time profiles. Okay. Okay, let's just see here on the chat. Okay, anyway. Okay, so we've got some temperature. We want to sketch out temperature versus time. And let's have a look then at the graph that's given to us. So here's the graph, and let's try and import that into the picture that we are working on. I'm just going to use the snip tool. Okay, so that's the graph that's given to us in the question, and so this is G of T, right? This is not R, so we are only given a plot of G of T in the problem statement, and then in the rest of the problem statement, we are given enough information to plot R. So we are given data down here. Right, so we are told K, T in, and TA. So sorry, it's actually so that's a K. So K, TA, and T in, and you can see those are all the parameters that are needed here to compute A and B. So you can calculate A and B, and then that defines that equation R of T. So the first thing, of course, to do then is to go and plot R of T. So let's say we do that. And yeah, that's my steady hand, right? Okay. So that's R of T. So let's say we plotted R of T and it looked like that. So R of T. And now we want to sketch the possible temperature time profiles. right? So we are saying then that that in this reactor, the temperature is going to change over time. So in this reactor, we are going to start at some temperature, and let's label it here T naught. So T naught is a special temperature. It's the temperature initially. So when T equals 0, so when we are looking at time equals 0, the temperature in the reactor is T naught. So what's going to happen is that temperature is going to change over time. So if you plot temperature versus time, you'll start out with some initial value T naught, and then something is going to happen here, right? So we don't know how the temperature, and this is the temperature in the reactor, right? So the temperature is going to vary in some way, and we'd like to estimate how it's going to do that. And we actually have everything we need to predict that from this set of curves here. So in fact, let's just move this down a bit. Okay, and I'm just going to erase this. Okay, and let's first comment on these graphs. By the way, are there any questions or comments on this so far? Okay, so let's think now about what it means in terms of what we are seeing here. So let's think about dt. Right, let's think about the rate of change of temperature. Now, if dt is positive, then that means temperature is increasing, right? And you see down here, we have temperature. So if temperature is increasing, then we are moving to the right here. And if you consider the relationships here, if your rate of removal of energy is more than your rate of generation of energy, then you are on balance removing energy from the system. You are reducing your thermal energy. So I'm just going to mark off the intersection points. So do you agree that in this region, so let's mark those points here. In this region, right, looking to the left of this point, your removal rate is always greater than your generation rate. Right, so on balance, you are tending to reduce your thermal energy, which means that your dt is going to be negative, right? And in fact, we should write it like that. We should say dt is going to be proportional to G minus R. And in fact, I think when we derived it in the notes, we wrote exactly that, right? We derived the energy balance and we grouped out the terms, the same terms that you saw in the equations there. And we had a G term and an R term, and it was in the form dt equals G minus R, right? So go back and have a look at that. But here you can see G minus R. So the blue line here is G and the red line is R. So if R is greater than G, dt is negative, right? That means we'll be moving in this direction. Temperature will be reducing, okay? And then looking to the right of this point, you can see G is greater than R. So here G more than R means that dt is positive. So that means we are moving in this direction. And so the system will eventually move here and then reach this point. And then if it tries to go past this point, you can see here that R again is going to be greater than G. And so R greater than G, dt is negative, and so T is going to be moving like that. Right, so when it says look for dynamics features on the curve, that's what it means. Right, you identify in which direction the system is tending to move. And so in a way, you could say there are just two dynamics features, namely these points of intersection. And so those are steady states in the system. And here you've got a nice stable steady state. You can see if your temperature rose for whatever reason, so let's say even environmental reasons had a role to play, that the day was just suddenly, the day went through a higher temperature. So the temperature rose for whatever reason. So if the temperature rose, then the removal rate rose and the generation rate dropped. And then that means that the system would be pushed back in towards that point. So even if you have a disturbance that caused the temperature to rise, the system would fall back to that point. And then conversely, if the temperature dropped, and again, it might be the temperature just went low on the day or something like that. If the temperature dropped, then again, your generation rate would rise and your removal rate would drop. The net result being that your temperature tends to rise, so it will rise back to that point. So you see here, this is a nice stable steady state. So a special, excuse me, in nonlinear dynamics, a special term for a stable steady state is an attractor. So we call this point an attractor. And then in this point, you can see, yes, you can call it a steady state, but the moment the temperature rises slightly, your generation is more than your removal, and the system will run away from that point. So it will run away up to this point here. And then if you were on steady state and the temperature drops slightly, then your removal rate will be higher and your generation will be lower, and so it will run away down there. So so we can say there are just two dynamics features of interest here. However, looking back at the question, we are asked to sketch the temperature time profiles. And if we do that, let's actually show these points first. So this point is around 570. So I'm just going to erase this. So let's put down here 570. And then this point is about 670. Yeah. So let's say 670 is here. And let's consider a number of initial states here. So again, going back to this picture of our reactor, if we consider that we started at some different temperatures here, so we could consider that we started at 500 degrees. So the reactor was initially at 500 degrees. Then we can see if we were down here at 500 degrees, then your removal rate was greater than your generation rate. So you were always reducing in temperature. So down here at 500, your system would actually be reducing in temperature. It would be doing this, right? And the same thing applies for all initial temperatures up to 570. So wherever you look to the left of this, you are always moving in this direction. So if you start here, it would be doing that, and so on. And so you could draw as many lines as you like in this region that are doing that. So all your temperatures are running off in this direction. Right, then exactly at 570, you do have a zero, there's no net change in your thermal energy. So you could draw a line like that. And we know it's extremely hard to stay on that line. So the moment you went above that value, then your temperature is going to rise, and it will rise up to this other value, 670. So again, I'm going to draw a line here. Oop. My hand's not that steady. If you hold down Shift in Photoshop, you get a straight line there. So yeah, if you started just slightly above 570, your curve would look something like that. And then for all values between 570 and 670, you would be falling up towards this line. And of course, you never quite reach that line, because the closer you get here, the smaller the difference, and so your driving force for temperature change reduces. So it's that kind of equilibrium diode that you see. Okay, so that's there. And then, as we said, the moment you go above that 670, you will be falling back into 670. So if you start higher than 670, you'll be going here and so on. Okay, and that's a complete description of everything that's possible in this scenario, right? So that's how you sketch these temperature time curves. A couple of things you could think about, if you wanted to be really precise with this, you could also consider how the distance between these changes. So you could say, look at 500, you've got a very large difference here. So your dt is an extremely large number, and so at 500, it would actually be quite a sharp gradient downwards. And then you can show that as you choose closer values, that the difference is smaller and smaller. So these gradients become more and more gradual. But I'm not too fussed about that. The main thing is, it should look like this, right? That you identify those two main features, and you show the directions that it's moving in that direction, and so on. Any questions or comments there? Okay, so that's the first part of that. And then it's saying here that it's known that the inlet temperature to the reactor fluctuates between 440 and 460. And we are concerned, right? So I'm reading here. It says here, it's known the inlet temperature to the reactor fluctuates between 440 and 460. And we are worried that that fluctuation might cause the temperature to run away to very low reaction rates and kill the reaction. So we want to know at what inlet temperature this might happen, and whether it's possible for reaction extinction to occur. Okay, so when and to understand this better, we have to figure out how inlet temperature comes into this, right? Where does inlet temperature influence the dynamic picture we've constructed? So if we look at the equations here, if you look at G of T, you don't see inlet temperature featuring here at all, right? This is entirely in terms of the temperature, which is hiding kind of behind this reaction rate. The other place, the only place we can see inlet temperature featuring is in R of T. But of course, this equation was for the simpler case. If we look at this problem, your R of T has T in occurring here. So it looks like T in doesn't influence the B part at all. So it doesn't affect the BT squared term here. So T in is only affecting our A coefficient. And if you look at what the A coefficient does, it's basically shifting our R of T curve around. So it's going to shift, so it's going to shift by 20 Kelvin. I guess the units of this A, that's something we have to figure out. And of course, this is a kind of empirical relationship. So we need some kind of constant here to correct the units so that it's in units of R. But anyway, we've got T in that's varying in this range, which means our R of T will vary in that range as well. And obviously I've put the numbers in and tried this out, and what I found is that it doesn't change this curve that much. So if you do go and put numbers in those ranges, then you find the curve doesn't, the curve just does this. Yeah. So at 460, it might be that, and at 440 or 420, whatever it is, it's somewhere here. So as T in changes, your R curve shifts, and that will shift, it will move these steady states, right? So this point might move here, it might move there. That means the actual temperature at which it happens shifts around a bit, and the same on this side. Right, so in terms of the numbers given in this problem, that's actually what happens. You could say that what the question is really asking is, do we have any T inlet value that actually does this? Right, and well, let's do it in a different, yeah. Okay, this one. So let's say we are worried about this happening. Right, so again, this is R of T, right? So if this is happening, if these two curves never intersect, that means there's no steady state available in the system. And that's quite different to some of the developments you've been seeing in your Chem-Eng courses, that you almost automatically knock out the DDT term and you solve for steady state. But you see, it's not always the case that you even have a steady state. So if your T inlet value was so unfriendly that it pushed the R of T curve all the way out here, and you never have a steady state, then what's going to happen is that no matter where you start, right? So let's say 400 and 800. Right? If your R of T curve was sitting up there, then no matter where you started, you would always end up just dropping in temperature like this. So your system would just drop to extremely low temperatures. And we know that reaction rate drops with temperature. So it would definitely be a complete extinction of your operation in that reactor. So what you could say is there exists a kind of threshold point. So there exists a point where my G of T equals R of T, right? And we'd like to know, so let's change the question a bit, right? In terms of the way the question is asked, there's not much happens, to be honest, right? In terms of the numbers that are given with the question, it just means your steady states move around a bit. So let's ask the more interesting question. Does there exist a T inlet value that we have to worry about? And we can say yes, that if we manage to get a value that caused us to be a tangent here, then that would be the point where the system is going to lose those two steady states, and we'd never the system would always be killed, right? We'd try to start up that reactor, and the temperature would just drop and kill the reaction. So there does exist this temperature T in where this could happen. So the question then is, how could we determine that value? And yeah, normally in my offline videos, this is where I would say, please take a pause, think about it, and then come back to the video when you've got an answer there. So maybe let's just pause. Could you propose to me, how could you find this number T in that seems to be so critical? So I'm fine with long, uncomfortable silences. Yeah. No takers? Where's the top man in the test? Are you here, Mohammed? Yeah, Mohammed Mansoor. Any answers to that one? see. So it's a different question. For temperatures less than 570, is the shape of the curve exponential and the same as above 670? Okay, so I guess this question is going to give everyone a bit more of a chance to think about my question, but let's answer this question. So I'm not sure that you can all see this comment here, but the question here is for temperatures less than 570, so for temperatures down here, is the shape of the curve exponential decay of the curve's exponential decay? I don't quite understand. And this and the same above 570. So for the temperature time curves. So in fact, I don't believe these are exponential decay curves. You see, the temperature time curves that I've shown, maybe they kind of look like exponential decays, but they are all entirely based on the difference between these two values, right? Between R and G here. And you see, these are not straightforward functions. This is some weird function here. This is quadratic. So these are not going to be, the result is not going to be exponential, right? So for your temperature time curve, remember, we've got dt equals g of t minus r of t. So each of these are going to change according to these curves. And the only time you'll get exponential decay is if you have something that can be written in the form k of, there might be another constant k minus t or something like that. So if you had a form like that, then you could talk about having an exponential decay. But clearly these don't follow. If you combine these, you won't get a form like this. So it's not going to give you exponential decay. Okay, let's just check the chat. Yeah. Okay, so I hope that answers that question, right? Okay, so thanks, Lavand. So Lavand is saying, find the coordinates where the tangent of G equals 0, where the tangent of GT is 0, and substitute those coordinates such that the tangent of G is also 0. So yeah, that's right. Okay, so if you so that's the answer to the question I was asking, which is find where these two curves are tangent. And by the way, they are not necessarily the way I've drawn them here. R of t is not necessarily, its minimum value is not necessarily where g of t is maximal. So in fact, R of t might be in some weird place like this. It might even be like that. And then that would be the same thing we are worried about, right? So that's right. You look for the tangency. So you get the two curves to be tangent, and then that would define that point. And then what you can do is you compare that with your original curve. So if originally when you plotted it, it was here, then you can look at this shift here. So this delta R value would tell you the delta T value, right? So let's say it again. So originally, well, in fact, you weren't there. Originally, you had two intersections. So originally, you were something like that. So you had two intersections originally. And then we are concerned about it becoming a tangent. So we shift up until we get tangency. And then the value of that shift, that delta R, is what we can use to determine the T in, the delta T in. And if you do that calculation, you'll see the T in has to shift by something like thousands of degrees before that happens. So no, it's not going to happen. So we can say here, no, we don't have to worry about complete extinction happening there. Okay, so any other questions or comments on this problem? Okay. Then question 2 is in a way similar enough that I'll just leave you to work that one out. Yes, I do have solutions, so I will be releasing solutions for this tutorial. Didn't really want to say that before. Yeah, didn't really want to say that now, but anyway. So the next question I wanted to look at was this one, and here it's in a way. It's not a very clever question. It doesn't, come up with anything new but it's something that you need more experience in. So in most of the problems we've dealt with, because we were still establishing the basic concepts, we didn't deal with a nice big problem, almost like design level style problem. Made me jump. Yeah, we didn't really deal with a nice big problem where we had to think through, issues of volume expansion and real unsteady state behavior and so on. So here's a nice problem that I just would like you to have experience with working through. So we are told we have a CSTR and we have this reaction happening. So A and B combine to give us C and D, and it's not equimolar. We get 2 Ds for every A that reacts here. So if you like, you've got 2 moles on the left-hand side and 3 moles on the right-hand side. So in a gas phase reaction, this means that your pressure, if it's in a batch reactor, it's going to pressurize and yeah, the pressure will rise as the reaction proceeds. Of course, in this case, it's in a CSTR. So the pressure might stay the same, but your volumetric flow rate will be different. So the volumetric flow rate in won't be the same as the volumetric flow rate out. And that's because your density is changing. Your gas density is changing because you are forming more moles. So that's one thing. And then we are given all the kinetics, or we are fully specifying the kinetic rate constant here. And I think we are assuming this is that this is an elementary reaction. So anyway, let's read it properly. We are given the heat capacities of each of the species, right? So these 4 species that's defined. We are given the heats of formation as well, and the reference temperature. So we know at what temperature those heats apply. We are given the molar masses of 3 of the components, right? So that's something we have to be wary of. So we are only given A, B, and C. So we need to somehow estimate the molar mass of component D. And then the CSTR is fed by the components in the following rates. So in this case, we are feeding in some of the product. So of course, we are feeding reactant 350 and 200 for A and B, but we are also feeding in some of C and D, right, 10 and 10. And we are given the inlet temperature at which they are being fed. And we are given the volume of the reactor, 50 cubic meters. Then we have a jacket around this reactor, and we have the overall heat transfer coefficient there. And then because of including all kinds of heat transfer geometry, we get quite a high heat transfer area, 200 square meters, right? In a 50 cubic meter reactor, we are getting 200 square meters. So if you think about the area of 200 square meters, clearly we need to be using lots of packing and things like that. And then unless told otherwise, the fluid in the jacket is 370 Kelvin. So that's because in this problem, I know we are going to say that the temperature changes at some point. So anyway, the default temperature is 370 Kelvin, and it's flowing fast enough that we can say the temperature in the jacket is the same everywhere. The reaction zone is initially at 200 Kelvin, and you are given the initial concentrations of each component. And note here the difference between initial amounts and inlet amounts, right? So in fact, let's start drawing this thing. Let's do a new one. So we are given, this is a CSTR. Come pen. Right. So we've got the CSTR, and we've got our little jacket here. And then you've got flow in and flow out. And we are given the inlet amounts. So we are told, and I'll just take the first one. So those are molar masses. So it's fed, so 350 moles per second of A. So FA in is 350 moles per second. 350. What is that? Yeah, moles per second. And then we are told the initial amounts in the reactor, 150, 100, 00. So in the reactor, we have a concentration Ca naught of 350. And what is that? Moles per cubic meter. So this is an error I've been seeing. I'm doing all this because I just want to emphasize that. Yeah. Okay. Thank you. Very nice. I'm busy now. Very nice. Okay. Okay. So here, this is the inlet amount, and so behind this, there's also an inlet concentration. So Ca in also exists. Sorry, this is 350. Are those numbers the same? 150 here, right? So this one is 150. So the concentration here is not the same as that initial amount, right? Your inlet concentration is generally quite different to your initial concentration. So just be clear about the difference between inlet and initial. Anyway, we want to develop from first principles the material and energy balances. So let's do that. Trying to take a better color here, right? So we know that the general material balance for a CSTR dNi dt is equal to, and if this is a gas phase reaction, right? So let's say all this is in the gas phase, then your V is constant. So if you were to write dNi dt equals ddt of CIV, then we could simply rewrite this as V dCi dt. Right? And then you've got flow in and flow out. So flow in is Fi in, and then flow out is your concentration here, and it's a CSTR, so the concentration at all points in the reactor is the same, including the point at the exit point. So the concentration here is the same as the concentration in the reactor. So we'll say Ci multiplied with the volumetric flow rate here. And we are going to specify this as Q out, which is generally not the same as Q in. So we need to say here Q out. Okay. Okay. Close my door, please. Okay. Okay. So that's flow in and flow out, right? So that's your molar flows, and then you have reaction as well. So let's. I think it says it's elementary. I can't remember. So if it doesn't say anything, right? So Yeah, I don't think it says it's elementary, but if it doesn't say it's not elementary, and if there's no further information given, then the best thing you can do is assume it's elementary. So we have to state that then as an assumption. Assume elementary. And then you can say minus RA, so the rate of consumption of component A. Well, there are cases when you can assume it's elementary, but if you are given information about if you are given other information that you don't by default assume anything is elementary, right? Just in this case where we aren't told anything, there's no way to solve this problem without a rate expression, we will make this assumption. But otherwise, you can't assume anything is elementary. But anyway, we are saying here minus RA is K, and then if you look at it, it's going to be KCACB. CACB. Okay, so we are doing this for the ith component. So we are going to say here minus nu I over nu A times minus RA. Let's just check if that works. So let's take component A. If it was component A, this would be nu A over nu A, which is 1, and then times minus RA. And the way we are writing it, minus RA is a positive number. So this would be minus this positive number, which is what we want. Right, so once more, let's talk through that. So here, if it's component A, then this would be a 1. And we know that this is going to be a positive number. Right. However, on balance, this whole thing needs to be negative, because if I is A, we know that the reaction is reducing the amount of component A. So the minus sign here is correct, right? And maybe we want to check that for some other components also. Let's say component D. So component D, we know nu D is 2, right? So if you look at the reaction, the stoichiometric coefficient here is plus 2. So you've got plus 2 divided by minus 1. That's the stoichiometric coefficient of A. So this is overall minus 2. So this is minus 2 times minus, so that's plus 2 times a positive number. And so that's going to be a gain of component D, which is what we expect, right? We are producing our product. Okay, so this form of equation looks fine to us. Okay, now we need to be able to solve this equation. So V is fine. We know we have a number for V. This is also fine because for concentration, that's the variable of the equation. Fi in fact, is simply given to us. So we are simply told all the molar flow rates into this reactor. So it's given somewhere here. So the CSTR is fed at these rates. So we are simply given the molar flow rates of each component. So all of that is known. Ci, of course, is the variable of the equation. So we expect that to be unknown. Q out is going to be a bit of an issue. So we'll talk about that one just now. We know the stoichiometric coefficients, and we have an expression for Ra in terms of the concentrations. So this looks fine. This is in terms of the variable. There is a kind of hidden variable here. So behind K, that's of course a strong temperature function. So we do need temperature as well, but we anticipate that we are also going to develop the energy balance and get dT dt. So we can see here, let me just move that here. So we can see here that we have a state vector, right? So we are going to have a vector. We're going to have a vector of concentration Ca, Cb, Cc, Cd, and T. And in fact, let's just call this the vector Z. So we have a vector Z of state variables, and we are going to be solving the equation dz dt. Right, so that's what we expect to do, and our understanding is that when we solve this equation, right, maybe we are going to solve it numerically. So we've got all these state variables. What's going on here? We've got all these state variables, and so at some instant in time, let's talk about initially. So here is t, and this is z, and these are the different elements of z. So at t equals 0, there are 5, right? So at t equals 0, we have all these. We know the initial concentrations, we know the initial temperature. So we have numbers for all these. And now these things are changing with time. So they are changing with time according to these differential equations. So we have differential equations, dc dt, we've got dt dt. So all those are sitting as a vector of differential equations. And so as we step forward in time, and hopefully you'll have seen some ODE solving with Suren, I think with Dr. Mudley in 3PO, right, in process modeling course. So you step forward in time by a certain amount, and then that defines for you the next value, and so on. So this is just my kind of homemade way of talking about solving ODEs. So you have an initial amount, you step forward by a certain amount using the gradient that defines new values for your state vector, and then you can do that again. So you can keep stepping forward in time, and that will span out your solution. So you get for each variable some kind of curve there, right? So that's what we are looking for. We are trying to develop our balances so that we can solve our material and energy balances and get how concentration and temperature changes with time. Okay, so so the reason I went into all that was to say that yes, RA looks complicated. We need temperature and we need the two concentrations. But you see, at every instant in time, we have all that. So if you pick any time, if you look up here, you have numbers for concentrations, you have numbers for the temperature. So at that current time, there exists for your current state, there exist numbers for all these things, and you just stick them in here in this expression, and then that gives you a number here. So in terms of understanding that this is a process, that we are going to solve all these equations together, we will be able to solve for these things. So this term also looks fine, right? That's what we were doing. We were saying, oh, that looks fine, that looks fine, that's fine. Now this part, we haven't as yet figured out how to solve, right? We need to be able to specify the exit flow rate from this reactor. And so to do that, we have to think about how is that changing with time? How is this exit flow rate changing over time? And to answer that, we can write our friendly mole balance on each of our species here. So we can say NC, we can say NA equals, of course, that's going to be NA 1 minus XA. Sorry, I should say NA naught. NB is NB naught, and we'll just use the stoichiometry. So it's minus NA naught XA. So this is telling us how much of A reacts, and we know that as much of that the amount of A, the amount of B that reacts is equal to the amount of A that reacts. So we know that's there. And then the amount of C, so we have NC naught, and we gain C. So as much C forms as A gets consumed. So this is plus NA naught XA. And then for D, we are feeding some D, and we know that twice as much D forms as A is consumed. right? So this is all true. And then we can add all this together. So if we add up all our components, so it's going to be, yeah, I don't know whether to, okay, let's just say Ni naught plus, and then let's add these here. So it's all Na naught Xa. So you've got minus 2 Na naught Xa plus 3 Na naught Xa.
I need your consent on a few.
This is going to be on balance plus Na naught Xa. In other words, your molar amount before and after, if you like, Na at, or rather Nt, right, the total number of moles, given that we have converted Xa, that's going to be equal to the sum Ni naught plus Na naught Xa. And then if we divide that by the initial number, so it's Nt naught, so that's the sum Ni naught. So this is 1 plus Na naught Xa over sum Ni naught. Okay, so that's how our moles are changing. Now let's think about what that means in terms of our volumetric flows. So if the pressure is low enough, of course, we can use the ideal gas law. So this is what we can normally write. And of course, this is referring to a gas that's just held in batch mode somewhere. And now let's say the gas was instead changing over time. So if it's changing over time, then if it's in flow, I mean, then instead of a fixed volume, we would talk about a volumetric flow rate. And instead of a fixed number of moles, we would talk about a change of moles in time. And then we've got temperature. Yeah, we've got temperature. So let's say that the pressure in the reactor is staying constant, right? So we are going to talk now about two states in this reactor, the initial state and the current state. So your initial state in that reactor, well, let's make P the subject of the formula, right? So P equals N dot RT over Q. So we can say that, and P is constant, right? So P constant with respect to time, we should say. P constant implies that N dot naught RT naught, your initial temperature, divided by Q naught is equal to N dot at time T, RT at time T, times Q at time T. And so your Q, we can say QT equals, so you multiply that and then you take that across there. So it's going to be Q naught, and then the R's can cancel. So it leaves us with N dot T over N naught. And then that's times T at time T divided by T naught at time T. So that's how you can correct for your volume, for your volumetric flow rate. So of course, we've done this in the notes. We did talk about the volume expansion term. So you can just use that theoretical development for volume expansion. However, we did it sort of the longhand way here so that we could think our way through this. So we can see for the ratio of the moles, you have this term. And then in terms of the temperature ratio, you can just take your current temperature. And remember, we said we can take the current temperature from the state variable. And then yeah, this was a bit silly. I should have just said T naught. You can't say initial temperature as a function of time. So here you've got your initial temperature. So all of that can be used then to estimate our flow rate exiting that reactor at time t. There's still a bit more work to this. We still need the molar mass, but we'll get there. So that's what you have to do. You have to estimate the change in your number of moles, because as your number of moles is increasing, your flow rate is also increasing. And then your temperature is also changing. So that also changes the density and hence the flow rate. So that's how you do that. And of course, you can only do this if your pressure is less than 15 atmospheres. That's where the ideal gas law holds. And if your pressure is higher than that, then you have to use a different equation of state, which you can do, right? Okay, so let's go a bit further now with this. So let's just write the reaction here. A plus B gives you C plus 2D. And here, if we think about using 1 mole, let's say 1 mole of A reacted with 1 mole of B, then that gave us 1 mole of C and 2 moles of D. And then if we wanted to know the masses that were involved, right, then we could say the masses then were the molar mass of A times that 1 mole plus the molar mass of B times its 1 mole. That must equal the mass that we had afterwards, right? So we are not, obviously, we can't create mass. So then we'll have the molar mass of C times that 1 mole that formed. So 1 mole and 1 mole completely reacted to give us 1 mole of C and 2 moles of D. So plus the molar mass of D times the 2 moles that formed. And so you can solve this for molar mass of D. It's the only unknown here. All these other molar masses are specified. So we have the molar mass of all the species, and hence we can translate between the molar flow rates. So we are given molar flow rates for each component, and through the molar mass, we can convert those to mass flow rates. So if we have that, and if we also estimate the density, so remember the density for a gas is PV, yeah. So the density, so that was, yeah, so it's P times the average molar mass divided by RT. So for a gas, that's how you can get the average density, right? So that's how you can translate your, so what's given to you is your inlet molar flow rate, and you can translate that into a volumetric flow rate through these things. And so you can then relate, so that then defines for you your inlet volumetric flow rate. And then we've talked about how to get these things. And so you can put all that together to get Q. So you see, there's a fair bit of work to get this Q out. Normally, we just we look at this kind of automatically, but here there's a fair bit of work to find out what your Q out is. Okay, so that's how you obtain the equation. After you've got this Q out, everything else is properly defined, or it's a variable of the equation, and you can solve this. We still need to define dt, but for that, I just want to pull up my solution. So for dt, you have to use this part, right? And I don't think we have shaft work. For Q, we have UA T minus TA. So let's just write that out here. So to estimate Q, the little bit of notation collision here. Q, let's call it small q for the heat transfer rate. So let this be heat transfer rate. So small q is UA T minus TA. Right, so be careful that you get the right delta T in there, because of course the heat being transferred is between these two things. Here your temperature is TA and here is the reactor temperature T. So that's the temperature difference. U is specified, A is specified, T is your state variable, and TA is given in the question. So you can get Q as a number. So that's there. I think that is not given, so we just take that as 0. And then the rest of these are just state variables. So your inlet molar flow rate is given, heat capacities are given, temperature is a state variable. Your reaction rate, we know how to estimate. Heat of reaction, you're given heats of formation and heat capacity, so you can estimate this. And then here, your number of moles, that's related to your state variable. So you take your concentration, multiply it by the volume, 50 cubic meters, and that's your number of moles. So everything is specified for the energy balance here. And so everything is fully specified. The moment you can get the volumetric flow rate exiting the reactor, everything is fully specified in these two equations, and you can solve it. Okay, and so all that is there. And then the simulation is shown here. And I just want to point out, yeah. So, and here there is a a variant on this problem you can consider. So we've been talking about pressure being constant. You can also think about, well, what if mass is constant instead? There's a difference to think about there. But anyway, if you apply all these numbers, then it reaches a certain steady state. But in part D, it says, what if after 12 minutes of operation, you increase your jacket temperature to 430? So you change TA to 430. And so the result is here. So let's just think about initially what's happening. So initially, your concentrations are actually, your component A concentration rises for a bit, even though it's a reactant. And that's just probably because your concentration in the reactor initially was lower than the concentration that you were feeding at. So you were feeding at a higher concentration. So concentration of A in the reactor just rose because you increased the amount of A that you are feeding to the system. And then your temperature also rose here. So then the reaction rate went up. So then component A started to reduce in concentration. And then eventually everything steadied out. So you reach steady state fairly quickly. And that's for everything, right? For concentration and temperature. And then your temperature in the jacket changed at 12 minutes, which is shown here. So your temperature in the jacket changed, and that caused your reactor temperature to go up, and then that changed the operation here. So clearly, this is the variant of the problem with mass changing. So in my solution, it's about mass rather than pressure being constant. But anyway, you can look at how to change that. And I just want to show how to include that change in time. So in your differential equation, right? So you can see all the work that we've been talking about. So here, it's saying for less than 12 minutes, use this temperature, and then beyond that, it's a different temperature. So that's how you can apply an unsteady temperature. You can just use an if statement in your differential equation. So this is Matlab code. And in the differential equation file, we are specifying all the state variables. And you can see here we are unpacking to get the mole fractions and all that. And then we reassemble all those derivatives and make one long vector. And so that's dy dt. Okay, so that's how you put together all those differential equations and solve this problem. So of course, a question like this, we don't really do in an exam and so on, but for a course like this, you must be able to do things like this, right? You want to be able to put together, it will help in your design type things. So you have to be able to look at the information provided, translate that into the equations that you've got, be able to incorporate any time information like that changing temperature, and then be able to solve those equations. Okay, any questions or comments there? Okay, let's now look at this batch reactor. Right, so this is the last problem we'll look at. So in this batch reactor, we have this reversible reaction in A and B. And so let's just do it down here. So we've got a batch reactor. So we've got A and B reversibly reacting. And we are given the constant, so we know how the kinetic rate constant is changing as a function of temperature. We are given the heat capacities, and number one, it asks us to draw the equilibrium curves. And if you look at some of my other notebooks, there is useful code for just for drawing your isorate lines and the equilibrium curves. Okay. One thing you can just look at quickly is E1 minus E2, right? The activation energy for the forward reaction minus the activation energy for the reverse reaction. It's 30,000 minus 41,000, so it's going to be a negative number. So this is an exothermic reaction. So we expect that in our isorate lines, the equilibrium curve is going to have a shape like that, right? So when we plot x versus t, it's going to look like that, and we are going to get our isorate lines that are varying like so. So, so we want to draw the xt plot, and of course you can see in the notes, and you've got enough experience in how to do that. And now we are told that this batch reactor is fitted with a jacket with a fast circulating heat transfer fluid. And we are given specifics about how it's operating. So we've got a jacket here. And the heat transfer fluid is circulating fast, right? The reaction itself stays in here. No material transfers into the jacket, but the jacket itself is fast flowing. Okay, now it says model the system, and the reactor is initially at 450 Kelvin. So I'm just going to go to my solution here. So in the first part, if you go ahead, you plot the equilibrium line and you pick a couple of ISO rate values of reaction rate values, then you can draw the ISO rate lines for them, like shown here. And then in part B, I need your. So in this part B, we are given the specifics. So we are told the reactor is initially at 450 Kelvin. So let's just copy this figure. Right, so we are told the reactor is initially at 450 Kelvin, right? So there's 450 Kelvin. And now if it's initially, that means nothing has reacted as yet. So conversion is 0, so x equals 0 and t equals 450. That means this is our starting point, right? And in fact, we know that there's going to be heating and all that applied. But before we go and implement heating and cooling, let's think about what the system will do initially. So we've got our reactor, and let's say we didn't have a jacket. What's going to happen in that reactor initially? So we know that we have the adiabat available in that case. So sum theta I CPI over minus delta HR T minus T in, or T naught in this case. So the gradient dx dt we know is this thing. And if we initially have none of component B here, then this is CPA, and then here is minus heat delta HR. So we know the system, there's going to be some gradient, which I'm not going to calculate now. But there'll be some gradient, and the system is going to be trying to run towards equilibrium, right? Now, what we are trying to do in this batch reactor is maintain the temperature in the reactor such that we achieve the maximum rate always. So we want to achieve a high reaction rate in this reactor. And number one, we need to understand, what is high rate then? And well, maybe even before that, if you drawn this adiabat, we can see the system left to its own devices can only do this, right? The system can't go anywhere else. That means the maximum conversion that we are stuck to is this value, right? Left to its own devices, the system is just going to go here and slowly fall into the steady state. And it's an annoying steady state. It's a very low conversion. We would like to reach these nice high conversions here. So we can think about just applying cooling to the system. So if we keep cooling, so let's say this is at one high temperature. So in the reactor is a high temperature, and then we apply cooling water in the jacket here. So we keep cooling that reactor. Then as we cool, we keep pulling the reactor back in this direction. And so if we apply lots of cooling very quickly, then instead of trying to go here, the system is going to be pulled. As it's going there, it's going to get pulled in this direction. And it all depends how fast we are cooling that. So if we cool very fast, it might do this. If we cool a bit slower than that, it's going to do this, and so on. So the thing I'm trying to say here is the action that we take in terms of the control strategy that we apply is going to determine the trajectory of our system there. It's going to determine along which line our species are going to behave in that reactor. So you see, in this jacket, we have control here, right? We typically have a flow controller, and that connects to some valve here. So if we apply a high rate of cooling through here, then that's going to cool this reactor down faster than if we don't use such a high flow rate. So by changing the flow rate here, we can change how fast we cool this reactor down. And so that changes which trajectory we'll be moving along. And that's important because we know that the rate changes so quickly along those lines. So there exists a maximum rate path that we would like to move along. So let's say that maximum, well, let's think about where that maximum rate path is. And of course, you've in the test and so on, you know how to do that. You could take for a CSTR, you can take your adiabat and look for the points of tangency, and so in a CSTR that's valid. So you would draw a maximum rate path like that. But now we are talking about a batch reactor. And in a batch reactor, the situation is quite different. In a batch reactor, in a way, things are more immediate. So in a batch reactor, let's think about if we are at a point here, right? So in our batch reactor, we've achieved a certain temperature and a certain conversion, and now we are sitting here. It so happens. If you were to use a lower temperature, then you'll be moving in the direction here. So let's say there's a lower temperature. If you apply a lower temperature, so for the same conversion, right? So we are talking about the batch reactor that has achieved a certain conversion X here, right? And we have one point here. And now for that same X, we could think about a lower temperature, which is here, or a higher temperature, which is here. And if we look at our numbers, right, on this red line, the reaction rate is 10 to the minus 5. On the green line, it's 10 to the minus 6. So 10 times slower on the green line. That means if we look at a lower temperature here, we are moving closer to the red line. That means it's a lower rate if we are moving to the left here. And then if we move to the right, again, we are moving closer to the green line and in fact the equilibrium zero line. So we are also going to a lower rate if we are looking in that direction. That means in the case of the batch reactor, the maximum value here is where we have the maximum rate. So in the batch reactor case, you don't have to draw adiabats and all that. You just go and look at the maximum point on your iso rate lines, and that defines for you the maximum rate line. And that defines also then the trajectory that we want to take. So we would like, we know we are here currently, and we want to get on this maximum rate line as soon as possible, and we want to stay there. So we could say, well, we could just let the system do its thing. So just let the system react, and it will reach the maximum rate line at some point. And so we could do a small integration here. We could say, okay, we'll let this be adiabatic, and we can see here the conversion at that point, maybe it's 0.18. So we can solve our material and energy balances until we get X equals 0.18. And then we say, well, now switch on cooling. So let's start cooling the system down now. And now we know what temperature we want to apply next. So we can say, okay, we reached there. Now to get to the next point, let's say that's there, we need to get to this temperature. So that defines how much cooling you must do. So you could go back to your material balance and say, okay, to achieve this conversion, this I can calculate is going to happen over maybe 20 minutes. So within 20 minutes, I need to cool the reactor back by that temperature also. So that tells you what duty is required on your jacket side. And so you can keep doing that. You can say, okay, now I want to get here. So that's here. And maybe it's 40 minutes by now. So I have 40 minutes to drop my temperature by this much here. So that's how you can create the locus of points that tries to stay close to the maximum rate line. And you'll do that obviously because you want to achieve your desired let's say we wanted conversion right there, 70%. Impossible to do it without cooling, you see, right? If you just left the system alone, it can only reach there eventually. If you apply cooling, then you can get here, but it depends very much on which trajectory you choose. So if you cool too fast, you're going to kill the reaction, and it's going to take forever for you to get up to this 0.7. If you cool along the maximum rate line, then of course you are going to get there in the shortest possible time. So that's what we are trying to do in this problem. We want to know the trajectory of of values to use here, right? And so we want to know what flow rate must we apply at the inlet point here such that we achieve the temperature profile here, right? There's a temperature profile here, T of T, that we want to accomplish. And we'll do that by adjusting the flow rate there. Right, so that's just describing at a high level how you do that. And in your solution, you'll see there's a detailed explanation of how you do that. And here's also a way to estimate the maximum rate path. So you can do it graphically just by reading off the maximum point there, or you could differentiate your rate equation. You can differentiate that with respect to temperature. So anyway, you've seen that in the notes. And here's what I got using my code. So I'm drawing the maximum rate line here, this green line. And you can see my actual reactor line. I get on that line, and then it stays fairly close there. And the way I'm doing that is here. So you will code up your material and energy balances. And here you see in the differential equation, right? If you look at this dc dt, and there's a dt dt here also. So in your material and energy balances, we want to know what the applied temperature is in the jacket. So here it's not quite the same as what I said. It's not just in terms of the flow rate. We assume that we can actually change the jacket temperature. So here I'm recalculating at each instant. I'm recalculating the maximum rate path temperature. So that means as I'm integrating along this path, I'm putting in again my new x value. So I keep putting in the x value to recalculate. So in fact, it's concentration. So I put in CB and CA, and I will get out the new temperature. And if my reactor temperature is below the maximum rate temperature, then I apply heating, and otherwise I apply cooling. And so this is a kind of, they call it bang bang control, because it's you are switching between, bang here, bang there. So you are switching between two applied temperatures. And you can see from the result that it's following the maximum rate path temperature like that. Okay, so in this problem, we are talking, we are not getting into the details like we did in the previous problem. We are now just trying to think at a high level what we are trying to do. So that's what we've got here. So follow these developments. You can follow in the solution, deriving your material and energy balances. So you can see the batch equation here, the energy balance there, and we are simulating those exact same equations here. And you can see it works. It does follow the maximum rate path. There is another variant to this. So instead of just adiabatically going to the maximum rate line, you could talk about applying heating initially to get you on the maximum rate line sooner, and then applying heating after that to stay there. Okay, any questions or comments on that? Okay, if not, I guess that's it for today. Oh, 1 second. So if the flow rate for cooling is too high, then it takes too long to reach the conversion. If the flow rate and the trajectory takes too long to reach conversion, by applying initial cooling instead. So, so in terms of this question, number one, yes, it might be the case that that the flow rate that you apply is not good enough to change the temperature in the jacket quickly enough. So in the code that you see, I'm just switching the temperature in the jacket, which is cheating, and I won't say a little bit, it's cheating quite a lot, right? We are assuming we can instantaneously change the temperature in the jacket, whereas actually we should be changing what stream we are using here. And it might in fact be that we have two different streams available. So you could use a high temperature stream and a low temperature stream. And if you want to get to 200, then you switch on the 200 and you switch off the 500. So you can do something like that. But there is still some thermal lag. It does take some time for you to accomplish that temperature change, even here, first of all, let alone there. So due to thermal lag, it might be that your flow rate changes are not fast enough. However, you can plan for that, right? So you know the maximum rate path beforehand. Because you have the kinetics, you can draw your iso rate lines and you can get the maximum rate path. And so if you know the thermal lag in your system, you can then apply flow rates that are far in advance of that. So you can because this system is totally predictable, because we've got the kinetics and we have the iso rate lines and all that, we can determine the trajectory required long beforehand. So that's one answer to this, right? You can derive all this beforehand and determine the required trajectory, first in terms of temperature there, and then temperature there, and hence flow rate there. So I'm just looking to see if the flow rate is high and the trajectory takes too long. So by applying initial cooling. So the question is applying initial cooling. Yes, I actually said applying initial heating, whereas in fact, if you leave the system alone, it's going to increase there. So you don't want to apply initial heating. You want to apply initial cooling to take you there. But the other thing you could say is, well, it's not as if nothing is happening down here, right? So if you consider points down here, you don't have to sit and wait for this to reach here. You could actually heat up the system to get on the line right here, right? So if you apply enough heating, you could jump all the way here where you have extremely high rates. So currently, maybe it takes 1 hour to go all the way from here to get on the maximum rate line. And you say, look, I'm not going to sit and wait 1 hour to get to where the action is. I'm going to apply heating to jump on the maximum rate path even sooner than that. So if you apply enough heating, then you'll get on there. And then it's an economic evaluation. So the time that you save by doing that, right? So you maybe it takes 1 hour if you just let it adiabatically get on the maximum rate line. Maybe it takes 20 minutes if you apply heating to get on there. So that saving of 40 minutes, that changes your productivity in the day. That means you can run your batch reactor many more times. Well, you can run your reactor more times, and so you can increase your productivity. So that increase in your profitability of that process, is that increase, does that justify the heating costs? And it may well do, right? If you have a heating coil in here. So adding a heating coil, maybe that adds a cost of 400,000 Rand to this reactor. And it might be that that saving in time translates over the year to maybe above that. So that would justify adding a heating coil. So does that answer the question there? Right, so these are all things that you can do. So if you like, in the first part of the course, we were focused on just getting to grips with the energy balance and being able to solve the material balance. And now we are able to think a lot more creatively than that, right? We are now able to say, look, I've got my iso rate lines. This is what nature is. And I can think about applying heating and cooling, and I can navigate this plane. So that's what we are trying to do in this section.